day in Chicago. Some people like the
See,
way
it's
it feels.
7:07, 17 seconds. It's Monday, the 4th of March, 2013. That was UTC, by the way. I'm throwing away my topology notebook. I looked at the Mobius strip. So I looked at 3 flip Mobius strips. This is just a Mobius strip with 3 flips, cut down the middle, transformed into a knot diagram. And I made up my own knot notation, but then I realized that I had to do some research and start using normal knot notation. So there's lots of different knots. You can see they're all permutations because they all have the same Jones polynomial. So because the boundary, the manifold is a loop with 8 twists and a trefoil knot in it. So there's only so many places that, like right here, this could be underneath right here. So this loop would be right here. So it would come over and under, and then it would come down like this. So you could just see how this could slip under there. So there's only so many ways the knots can be mutated. And so here's all the knots. And then I was trying to find a way to count the knots. I was looking at all the topology of Eulerian and planar and directed graphs and graph theory and directed graphs. And I discovered for myself the Whitney trick, which is how it's taken apart. For example, why do some knots have a trefoil knot with 3 twists, and some are a non-alterating figure of 8 knot with 2 twists? So I'll show you the difference. Jones polynomial, 1984. Stephen Small, I think, did that. Smith conjecture. Smith conjecture? Finding the minimum number of vertices. I can't remember what. Well, here's one flip Mobius strip. It's just a standard Mobius strip with 1 twist and taped together, so the A edge connects to the B edge, so there's no boundary. When you cut it down the middle, it gives you 4 twists, and the 4 twists can be cancelled with two crossings. So each crossing cancels, right? 2 twists each. That's 4 twists there. So the number of twists after, and I found this out, the number of twists after a Mobius strip is cut down the middle is 2n plus 2. So 1 times 2 plus 2 is 4. So with a 3 flip Mobius strip, it's 3 times 2 is 6 plus 2 is 8. But then it has the trefoil knot in the manifold. But then when you think that each one of these crossings is 2 twists cancelled, look how it breaks down with these. Look, 1, 2, 3, 4, 5, 6. So 6 times 2 is 12. So there's, and then it's like, if these are 2 crossings here, that's 2, 4, 6. So that's 6 twists canceled by the 3 loops, but then we still have 1, 2, 3 crossings, so it doesn't add up. And I found that when you take them apart with the Whitney trick, so for example, a Whitney trick, I think Stephen Small used that. Like right here, you couldn't pull this apart because you'll get a pinch point right there. However, if this straight across here was invisible, you could back this off across it, and that's a Whitney trick. So you've unconnected these 2 points without making a pinch point, if that makes any sense. So when you take them apart with Whitney tricks, you get the unknot for the figure of 8, the non-alternating figure of 8 knots and the trefoil knots. You get the unknot, but there's a special manifold. There's a special one. And then I looked at all of the 1 flip Mobius strips. They only make 5 different knots. The Jones polynomial. I don't know what I'm going on about here. Look, here's the Whitney trick. So here we go. Coincidence. Look. See? Here it is. Here's the non-alterating figure of 8 knot with 2 twists. And here is the trefoil knot in the middle with 3 twists. So look. If this vertical bit is invisible, we back this off, and then we got here. And then if all of this right here is backed across this horizontal section, then we get this knot. And then if this is invisible here, we back off, we get the unknot. So again, look, here's the Whitney trick. You can see this little loop right here is unconnected, it's pulled out, and there it is there. And then you do a little, put it over itself, you get this, you get the last little loop in it, 2 loops actually, and then you put this over this side here, and then you just back it off. You get the unknot. But this one, this foil braid knot, which is special, because when you get the manifold, when it's cut down the middle, if you flip one of the braids around the whole thing, it makes all the boundaries point inward. So this is the black surface. These are all black surfaces, and all the outside is all the white surfaces. So you totally change the knot by flipping one of the coils over itself to get it what I call the braid knot. There's only 2 braid knots. And when you take this apart with Whitney tricks, you can see we take the center out. We don't get the unknot. We get 4 twists. And now you can see the 4 twists. And we know that each twist, each crossing, each loop is 2 twists. There's the 8. Now we can see the 8 twists that are left in the knot that represents when the 3-flip Mobius strip is cut down the middle, and that kind of flipping the manifold over itself kind of gets rid of the trefoil knot, if that makes any sense in a higher dimensional space. It's beautiful. And there's more Whitney tricks. So that's my book. It's going in the bin. Oh, well, here's some more Whitney tricks. Here's the 2 different. There's one of them. Oh, but that has a different Jones polynomial, so I think that was a mistake. I know I cut one of the Mobius strips and put it back together, so I think that was a mistake. So I don't think that is not actually a Mobius strip. There's only one braid knot, which is this one. So because they all have the same Jones polynomial, and this one has a different, it's VT equals 1, that's a mistake. That's not from the Mobius strip. That's my mistake. And here's me trying to understand the nature of the twisting of the manifold, the strip. Here's the Jones polynomial. This knot here is the Lorentz knot. It's from the Lorentz tractor, and it's nested in the Mobius strip, which I found. And there's the Jones polynomial for it. And here I'm looking at Jones polynomials for the knots. You can see the braid knot, the non-alterating figure of 8 knot, and the trefoil knot, they all have, do they have the same Jones polynomial? This one here is an error, but it's like t to the minus 4 minus 3 minus 1, or it's t to the 1 to the power of 3 to 4. So they're opposite. So you got to bear in mind that some are left-handed and some are right-handed, because when I put it's either I flip it this way and tape it together, or I flip it this way and tape it together. So the knots are chiral. So I think the fact that they're backwards is the chiral nature of the knots, basically. So they're the same Jones polynomial, except one is chiral, left-handed, one's right-handed. And then I found another manifold. For example, when you get this knot from a 3-flip Mobius strip, and when you switch the crossings of the trefoil knot, so here it's under, and there it goes over. You can see here it comes under, and then here it goes over, and here it goes over, and it goes under. So we switch we made the trefoil knot backwards, and we get this new manifold. But when you put the edges of it together and give it a kink, you get this propeller manifold, which is different than a Mobius strip. And I don't know the name of it, but it has a name, but I can't remember. I did that in my head one day, and then I looked at paper models and I had a eureka moment. So here's the 1-flip Mobius strips. These are all really nice. Symmetry. This is my favorite. That's how elastic band falls on the ground. And I've seen 2 today by chance. Oh, I don't know my notes on pinch points, handshaking lemma. The handshaking lemma, in any graph, the sum of all the vertices, vertex degrees, is equal to twice the number of... is this my work, or is this general topology? I forget. I spent like 900 hours studying topology. I was completely obsessed with it. So this is going in the bin. We're closing a chapter on my life in topology and knot theory and the Mobius strip. There's the Mobius strip. You can see that's what it looks like. See, you give a half snip and the boundaries cross each other. Not the boundaries, but the edges cross each other. And here's the braids coming up. These are beautiful. That one's a fake, remember. What does it all mean? Really? It's just to occupy my mind, really. Oh, here's a Mobius strip. Look, here's the 8 twists. The 8 twists get canceled. Look at this, beautiful. Look at the symmetry. It's flat, and look, if I take it apart, Oh, it's just look. It's just a loop of paper. It's not even a Mobius strip. Sorry, I was tricked by it. But I do have a Mobius strip here that can get flattened that way. Believe it or not, a Mobius strip can be flattened to look like that for some weird reason. Even with a trefoil knot in it, when you organize into the braid, you can flatten it. I should have it taped on the page here. I'm surprised. I thought that was the Mobius strip because I recognized the topology of the folds and how it flattened. Oh, these are nice. These are a little family in their own. Here's more of the knots. So this is just a journey through the Mobius strip topology. Oh, here, that's one of them. That's what it looks like before it's cut down the middle and it's been flattened. I drew that. That's what it looks like there, flattened. But I don't have the actual paper model, which would be nice to lift it off the page. So, oh, here it is. No, okay, that's it there. But I drew that. It's not even like you want to pick it up and take it apart. You can see we're now in the plane. And look at the crosses. You can see, look, 1, 2, we're down this way, we're up this way. There's 1, 2, 3, 4, 5, 6, 7. There's 8 folds. And there's a trefoil knot in it, I'm pretty sure. Wow. You can see the beauty of the trefoil, of the Mobius. Oh, God, what am I going on about here? Anyway, that's enough on the Mobius strip. This is going in the bin. Okay, Mobius strip, goodbye. We're saying goodbye. I'll save this page though. This is my summaries of my work. That's what we'll save. These are nice pages to save. No, I'm not even saving anything. It's done. Done. Bye, Mobius. In the bin. Oh, no more topology.